Okay, so I got a little ahead of myself, and let's talk about this concept that Einstein has, that the speed of light doesn't change if you change reference frames. That there's something wrong with the Galilean transformation. Let's just see, because of course in 1904 or 1905, when Einstein predicted this, it was clearly not well accepted. It's ridiculous, right? So let's just think about the series of things that had to go into thinking about this. So first of all, Maxwell's equations do not show the same physics. That's postulate one. Remember this postulate about that the same physics has to be the same in all inertial reference frames in a Galilean transformation. So Maxwell's equations don't work in a Galilean transformation. And as a matter of fact, Maxwell's equations predict that the speed of light is frame independent. In other words, c equals 3 times 10 to the 8th meters per second, those constants that come out of Maxwell's equations, relative to any observer in any inertial reference frame. Well, that just sounds weird, and so one should question that. But that was one of the conclusions that came out of Maxwell's equations. Right? This is silly because obviously light, a disturbance, has some medium that it travels through. Now, what's the point here? What's the underlying point here? Remember that Maxwell's equations say that light is frame independent. But if light has a medium that it travels through, and that, whoops, what happened there? And that medium is attached to some frame of reference, then light clearly has a preferred frame of reference, and it should move like a Galilean transformation relative to any other frame. Let's just think about what I'm talking about here, right? So let's just think about other types of waves. Think about other types of waves. Now, maybe I just gave it away by showing you some pictures, but any type of wave, right? And the standard ones that we can come up with are maybe a water wave and a wave on a stringed instrument, right? And then also I always like to talk about the stadium wave, because the stadium wave is indeed, the people waving their arms up and down, is indeed a wave. It's a disturbance that travels through a medium. And think about those waves, right? Oh, I did it again. Why did I do it again? Wait a second. Okay. Sorry, reset. So now let's take a water wave, for example. A water wave is a disturbance that happens in what medium? The medium's water. So it's a disturbance that propagates through water. And water has a frame of reference, right? So if we're talking about a pond, that pond is stuck to the earth, and so the earth is the frame of reference of that water wave. Or if you want, if you're on a train and it's a water in the sink on the train, well then or in your water bottle on the train, then the frame of reference is the train, right? So it has a frame of reference, and all other frames of reference move relative to that one. So the wave travels through a medium which has a fixed frame of reference. The next example, right, is the stadium wave. Now see if you can make the same argument for the stadium wave. The stadium wave is a disturbance that travels through people. People stand up and sit down. And that stadium wave does have a preferred frame of reference. It's got a frame of reference through which it moves, and the frame of reference is the stadium, just like the lab. Right? The stadium is stuck to the earth, and so it's the Earth's frame of reference, or the stadium's frame of reference, or the lab's frame of reference. If you've got a frame of reference that you can identify, then other frames can move relative to that frame, and the Galilean transformation should work, theoretically, at least in 1904. Okay, before Einstein came around. Okay, so, and then of course there is the string wave on a musical instrument. This is a kind of a cool picture taken with in a special way. These are real waves on guitar strings. And so now think about the string wave, right? The string wave on a musical instrument has a frame of reference. And what is that frame of reference? The frame of reference is the guitar string, which is stuck to what frame? The guitar. The guitar is, if you're in the lab, it's in the lab frame. If you're on a train, it's in the train's frame, but it's got a frame of reference. It's got a medium that is going through that's stuck to a certain frame. The other one, of course, you probably thought of, which I forgot to mention, is the sound wave. A sound wave. What is a sound wave? A sound wave is a disturbance, right? All waves are disturbances that propagate through mediums, I think. Sound wave is a disturbance that propagates through, typically for us, it's air, right? It propagates through air. So make sure you understand that sound cannot propagate through a vacuum because there's nothing that can oscillate. There's no frame of reference. There's no medium for sound to travel through a vacuum. In space, no one can hear you scream. It's a famous quote from a movie long before you were born. Okay, so sound wave, back to a sound wave. A sound wave is a pressure wave. It's a propagation of pressure. It's a disturbance that propagates through air. Of course, sound can travel through other things. It can travel through walls. It can travel through water, etc. So it's travels through whatever, but typically we hear sound through air more often than not. So let's just say one of the frames of reference for sound is the air. And the air is pretty well stuck to the earth. So it's in the Earth's frame of reference, although that's not quite true. If it's a windy day, have you ever tried to hear somebody on a windy day? If you stand in front of them in the way that the wind is blowing from the person, you can hear them quite well. But if you stand behind them, you can't because the sound is in the frame of reference of the wind and it's being blown away from you if you're standing opposite direction of the wind from the person. But the medium that it travels through is the air, and that air has a given frame of reference. So clearly, light should have some frame of reference, should have some medium that it travels through. And the question is what is that medium that light travels through? So the question we need to ask, and the question that Einstein asked, is what is the medium for light? If we can identify the medium, we should be able to identify the frame of reference in which light travels. And maybe it's just that light travels so fast that it's really hard to make these relative measurements of light speed. It would be in 1905 really hard to measure changes in light speed from 3 times 10 to the 8th meters per second to a frame of reference which is 3 times 10 to the 8th meters per second plus 30 meters per second. Wait a second, let's make sure you understand that, right? If I have light which is traveling at c equals 3 times 10 to the 8th meters per second, and we're saying that if I'm in a car traveling at v equals 30 meters per second, then the light should be traveling at 300 million and 30 meters per second relative to the car. We're not going to be able to measure that change in 1904, 1905. 1905 was the year of Einstein's Annus Mirabilis, the year of miracles. So maybe we're just not able to measure the changes that come from a change in frame of reference because light is so fast. So in order to answer this question, of course, we do have to know something, which is simply that Maxwell had just shown in the late 1800s that light is a wave. So prior to that, light we've known has existed since we have existed. We have understood this concept of light and that the sun brings us light. Originally, for the Egyptians, it was the sun was the eye of the god Ra, and it was the eye of the sun. And at night he closes his eye, and in the daytime he opens his eye. But we've always understood the existence of light, but we've never understood until the late 1800s, until Maxwell, that light was a wave. So now that we understand light as a wave, now we need to start looking for the medium. What waves, right? When I say what is the medium, there is a disturbance that propagates, just like the water wave propagates through the water and the stadium wave propagates through the people, right? And the string wave on a guitar propagates through the string. There's a disturbance that propagates through a medium. What is the medium for light? Now, you say, oh, but light, we didn't even understand it was a wave prior to late 1800s. So, because the waviness was invisible. All we could see was light. Light, there's nothing obvious that makes it a wave. It was invisible. So maybe the medium for light is invisible. So that's what I'm trying to get here, is that maybe the medium for light is invisible, so it's going to be hard to find. And if we can find that medium, If we can identify that medium, we can identify the frame of reference, and then Maxwell's equations need to be fixed. Remember, one of them needs to be fixed, either Maxwell's equations or Galilean relativity. So let's go ahead and take a look and try to find that medium for light. So prior to Einstein, it was certainly understood that light traveled through some medium just like everything else does, and that medium was given the name the ether. The ether, but it was an invisible medium, or something we couldn't see. Now, there's nothing unusual about that. Today we have things that we can't see that we discover, right? I mean, the most recent, of course, really big discovery was the Higgs boson, the particle that physicists had been searching for many, many years, and finally found, detected the Higgs boson, which is the thing that accounts for mass. That was one of the biggest discoveries of the century, of course. But anyway, if you don't know anything about that, you should go read about it. Google it, Higgs boson. In any case, having invisible things is not unusual, right? X-rays are invisible, yet the X-ray was discovered in the early 1900s and well understood and very quickly used. In any case, so the ether was this medium that light travels through. So what do I mean by that? Well, let's say we have a light wave, and again, we can't see the waviness of light very well, but we know it's a wave. Let's say we have a light wave. That light wave must be waving in some medium. There must be some medium that the propagation is going through that carries that wave, and we call that medium the ether. And so let's just pretend we can, let's just illuminate this ether. And so now, if the light wave is traveling at c, we won't write down the number, at c relative to the ether, and then the ether is traveling at v relative to the lab, then the speed of light is going to be c plus v relative to the lab. I'm not going to write all those words, you get it. If light is traveling at c relative to ether, and the ether is traveling at v relative to the lab, then the light must be traveling at c plus v relative to the lab. It's like saying if there's a string wave on a string and a guitar traveling at, I don't know how fast they travel, pretty fast, but let's just say it's 300 meters per second, but the guitar is traveling down the road at 30 meters per second, then the wave on the string is traveling at 330 meters per second relative to the road. Okay, so there must be this ether that we just can't see. But if there is an ether, we got to have a way of detecting it, so we're going to look for the ether. So this occurred long before Einstein ever thought to, or at least published, the idea that there is no preferred reference frame for light, that if light was discovered as a wave in the late 1800s, then the next step would clearly be to figure out what was waving, right? What was the frame of reference in which light was a wave? And so these two scientists, Michelson and Morley, did what's now known as the Michelson-Morley experiment in 1887. The experiment was an ingenious experiment in interferometry. Interferometry. It's an R. It's important in many ways that we understand the experiment and we understand interferometry in particular because interferometry is a scientific method that is highly used today in order to make very careful measurements in a lab. So we are going to spend a day or more, talking about interferometry and the Michelson-Morley experiment. In order to understand interferometry, interferometry has built into the word interference, right? Interference. We have to understand interference of waves. You should know a little bit about interference of waves, but let's just take an aside here and talk about the interference of waves.